Good day, everyone. Can I just please get by a show of hands if you guys can hear me? Thank you very much, Samkelo. Thank you. All right. Good day, everyone, and welcome to you all. Thank you once again for joining us today. My name is Busisiwe Madeo, and I'm going to be your host for today's session. So before we begin, just a few quick reminders, please. If you could just please keep your microphones muted. Then feel free to please raise your questions in the chat box. These will be addressed at the end of the session. Please also note that slides as well as the video will be shared with all attendees. And for attending today's session, you'll also be eligible to receive an attendance certificate. You'll see towards the end of the presentation, there will be a slide that will be displayed. There will be a QR code on the slide as well as a link. Please use those to access your attendance certificate. Again, it is a pleasure to welcome you to this session in our Power Series. So it's just the next session in our Power Series, hosted by the Engineering College of Science and Technology. This is our third webinar exploring the Power Series. So just a little recap of our previous webinars. We've explored the fundamentals of power systems, the integration of renewables, and the role of smart technologies in modern grids. In today's session, we will continue with that journey, but focusing on the critical enablers of energy transition. Today's session is on energy storage as well as grid flexibility. So, as power systems become more dynamic and renewable driven, the ability to store energy and respond flexibly to change demand is no longer optional, it is essential. Today's session will unpack how storage technologies and flexible grid solutions are shaping more resilient, reliable, as well as efficient power systems. It is my pleasure once again to present to you Mr. Samkelo Nene, who is going to be your presenter for today's topic. Again, Samkelo Nene is a lecturer here at ECST and is very knowledgeable on these topics. Samkelo, over to you.
Good day, everyone. I hope everyone is good and you're able to hear me. I'm audible.
We can hear you, Samkelo.
Thank you. So, thanks for joining us once again, everyone. Let me take control. I see Lucy what she did there. She just threw me in the deep. I'm an expert in these things, apparently. um, of which I don't consider myself as. So, I'm also a student of life. We learn every day. So, welcome to our webinar series on power systems. So, this is our last webinar on this series. Obviously, in future, we will come back and touch into specifics in what we have covered in this webinar series of power system. However, so far regarding power system, we have done sort of high level presentation as will be today's, which was on power systems. So we started with fundamentals of power systems, where we um, looked at the grid from generation to transmission to distribution and loads. And then the second webinar, we touched on the integration of renewable and the impact it has on the grid. And then the last time, we touched on smart monitoring in terms of using smart grids to ensure resilience. And today we'll focus on energy storage and grid flexibility in power systems. So these are the list of contents. We will sort of have an overview of energy storage technologies. We'll compare and then look at their role in grid operations. And also we'll look at grid flexibility, which is an important part of the modern grid. The modern grid has to be flexibility and also in terms of coordinating the planning, and we'll look at some economic and policy consideration and some of the examples. So in essence, today we'll, as we already saw the list of content. We're looking at overview of energy storages, whether it's electrical, whether it is chemical or mechanical, and then obviously their role in terms of grid operation. And then we'll also reflect on flexibility. Again, as I've said from our previous webinars, we are on power systems, from fundamental to integration of renewables to smart monitoring, and then today into grid storage and flexibility. So why is this important? Why this is so important, especially in the modern grid? Um, anyone could quickly type on the chat why this is important. So again, we learned with the integration of renewable that they are not dependable. They vary, so they introduce variability and uncertainty. So then energy storage sort of then becomes a bridge between the intermittent nature, the inherent intermittent nature of renewable. It becomes a bridge between that and the reliable supply. And then grid flexibility is important for the grid. So flexibility is really about the grid's ability to adapt to this variability and uncertainty, which is uh, inevitable, especially with the increase in renewable capacity additions. So starting with the typical or energy storage, the first is being the conventional storage, which is the pump storage. So, or the hydropower storage. Also, we have the hydropower plants, which then operates on the moving water. You'll have your turbine. There'll be a moving body of water. So that's your typical hydropower plants. That's just used for your generation of electricity. However, when you talk about storage, then we talk about two reserves. So it's sort of it's the same concept or the same approach where we use water to then generate kinetic energy to drive turbines, which then drive generation. So the concept of hydro power plants is then used when it comes to pump storage. As we see here, we have two options. The first being the open loop, where the lower reservoir uses an open flowing, basically, water. So what happens then during off-peak times? Let's say we have less demand on the grid, we have too much generation. Then what it does, then the generator, or rather the pumps with the motors, this becomes a load connected to the grid, which then uses the excess generation to drain, uh, to pump the water up the upper reservoir to store it. So that when during the peak demands, then the water is released from the upper reservoir, and then that water then drives the generators, which will then, sorry, the turbines, which now would drive the generator to supply the electricity. So it's a matter of give and take. And then the closed loop is for obviously countries like ours. South Africa is one of those countries that are semi-arid. We don't have that abundant flow of water to use or to have hydropower plants. So you find that we have about three pumped hydro storage power plants where we have two reservoirs. So the lower and the upper reservoir. So here, if you look here down here, this is a closed loop, this entire system, by the way. So the water that is here is not a water of it's not a flowing body, right? Rather of water. So then again, yet it's the same principle of give and take. When we have excess generation on the grid, then we pump the water. So this becomes a motor to pump the water up the reservoir. And when we have demand, then we release the water. Then this becomes the generator, which is driven by the turbines that converts mechanical energy into electrical energy. So this is one of the, or rather, it is the most established power storage in terms of large scale power storage. And here's an interesting question if for anyone who might wish to comment, or we can also reflect this at the end of this webinar, why this storage has remained dominant for decades despite newer technologies. I think perhaps we will have more answers as we get to unpack the other technologies. And then coming to battery technologies, so we have lithium ion, we also have flow battery. With lithium ion batteries, in a sense, they operate by moving lithium ion from cathodes to anodes and so they store electricity, which is chemically, if we were to think of it, is it mechanically? But with the batteries, it's more of like chemically. That's how they store energy. So you also have flow batteries, which also uses electrolytes. So with the lithium ion, you move the lithium ion from cathode to anode through the electrolyte. Whereas with the flow battery, which also uses electrolytes, you have a sort of like a cell stack that stores the energy. So the difference between the two is that with the flow battery, they're easy to scale up, and also in terms of power density or energy, or rather the energy density, lithium ion has high energy density, and also it stores itself its power in compact cells. So lithium is more applicable for your for your vehicles, and also for like, if you were to think of grid balancing, then it's for like short duration. Whereas with flow batteries, since they're easy to scale up and also their flow dense, or rather the energy density is low, so then they are more suitable for stationary application. If you were to think of then long duration grid stabilizing. And then moving on, this is still the flow battery. And then others, if you were to think of the solid state, which is still emerging technology. So solid states, if you were to then compare it with the lithium ion, if you were to look the two, where we have the electrolyte here in between the cathode and the anode, for solid state, we have a solid material. So why we have this material rather than electrolyte? So what it does, obviously, then it eliminates the potential of a leakage, since this electrolyte is a liquid, and also it reduces the fire risk. However, it is still in development, but the prospect of it are positive, since it has this benefit when you compare it to lithium ion. However, if you're to look in the markets, lithium is still dominating, because obviously solid state, the still challenges regarding scalability, regarding manufacturing costs. And then the other one is hydrogen storage. Hydrogen storage is one of the, or rather, hydrogen itself is one of the interesting energy carriers, because hydrogen, it's cross-cutting energy carrier. So if you have to think of storage, then you then convert electricity to hydrogen. So that obviously those who have done chemistry and chemical, if you were to talk along the lines of electro electro water electrolysis. It's water electrolysis, right? I almost got that wrong. So basically, to separate hydrogen from oxygen, H2O. So there are different types of processes. You can do that using renewable, which we call green hydrogen, or you can use your coal powered, or power from coal, which we call what's gray hydrogen. Now there's also pink, which is powered by nuclear. So there are different colors, but it's not really about the color of the hydrogen, but it's just talks to the source that it comes from. But in essence, you're converting electricity through that electrolysis, water electrolysis process. So with hydrogen, it's different from battery, because obviously with battery you're storing power chemically, and also as an electric charge, directly as an electric charge. Whereas with hydrogen, uh, it's more of like an energy carrier, which then can be also be used for fuel, transportation, um, and also if you then were to derive hydrogen, a step further, you get ammonia, which is used in agriculture. Hence, I said it's one of those interesting sources that is cross-cutting, that can be used for for heating, can be used for fuel, it can be used for agriculture and so forth. So you convert this into hydrogen, and then when there is a demand, when it's required, then you can burn this as a fuel, and also obviously then you can then use it via fuel cells. And then the one that's uh, on the top right is the flywheel energy storage. So flywheel is more of like mechanical. As we see here, we have a basically a rotor. So what happened is that when we have more power than we need in the grid, then obviously the motor drives the rotor to keep it spinning at a healthy momentum. So this is a vacuum, obviously, to take care of the air friction and the drag. So it spins, and then whenever then the demand exceeds the generation, then the motor sort of then turns into a generator, whereas now the this rotation then drives the motor being a generator to inject power into the system. But however, this is for for short term because it can last from milliseconds to minutes. So it's for rapid response to the grid. If there is just a small surcharge in the grid and then it's just balances that. And then below we also see ultra capacitors or capacitors. Um, Also, they are also just as with the flywheel. They have high power density. They discharge quickly. However, unlike flywheel, which is mechanical, ultracapacitors are more like of electrostatically. So it stores charges between two plates, and then it discharges instantly. And you'll find it is used a lot in electronics when you wanna stabilize the voltage, which is a topic that we will start. The next segment will be on electronics. So we will come back and revisit capacitors and ultracapacitors. And then the other interesting storage is the compressed air energy storage. So this one, compressed air energy storage it also uses electricity. However, then to unlike hydrogen, where you then convert it to hydrogen, here we compress air, and then obviously it will be compressed to a high pressure and then stored underground. So it's a tank or either an underground cavern where we store the air. And then when there is a demand in the grid, what we do then, we reheat the air to expand it, and then we drive the air, or rather, we use the reheated air to drive the turbines, as you would in a normal steam power plant. For example, if you to think of a coal plant, what do? You burn the fuel, right? You burn the coal to get the steam to drive the turbines to generate electricity. However, with this one, we're using electricity when there is more generation exists demand, we use that surplus to then heat the air, and then we store it here, and then when there is a demand on the grid, then we release it. However, we have to reheat it. Traditional compressed air energy storage, they use natural gas, which one could argue that that sort of contributes to emissions. However, with this one, you have to have a space underground to store. Hence, it's not that common. However, it is suitable for large scale, as would as pumped hydro is. So, and on the right parts, then you get system that has like hybrid, has a mix of supercapacitor, has a mix of lithium and pumped. It all depends on the application, obviously, then which you will use for short duration and long term. And then this is a comparative chart. So sort of compares, excuse me, each technology. So based on the technology type, as we see here, we see that the yellow those are electrical storage, and then these are mechanical in gray, and then we see the chemical, then electromechanical, and also in terms of their power rating and also in terms of their discharge. You see these one-year high capacitors, as we said, and also flywheels, they discharge in seconds. And then as you go up, lead acid batteries in minutes, and then hydrogen, lithium ion battery, and pump hydro, those are more for long duration. So this is a good chart then to determine which storage you want to use for which application. So that was regarding the technologies. And then going on to the role of the storage in the grid operations. Again, we've just saw the chart of different uh, storages, which then when we look at the frequency regulation, then they can serve as like reserve products or responses to the change in frequency. We touched on this when we were on our second webinar on integration of renewables. We touched on this frequency regulation. So these storages or these technologies, then we can use it as our response or reserve product. So starting with Initia essentially is as we said the last time, is that it's simply resistant to change, in particular the rate of change of frequency of the system. So this is normally provided by the synchronous generators. So they have inertia, the spinning generators, they have inertia that tends to then resist the change in frequency. And then we have other forms of primary and fast response, which can be in a form of injecting power, or just looking at the synchronous generators. What they will normally have, they'll have governors. Obviously, that will pick up the drop in frequency, which will then send information to generators to then increase the generation accordingly if there is a drop in frequency, or to reduce generation accordingly if there is an uh, increase in frequency. And so as you go up, then it's a matter of adding other types of storages. So again, just as you see here, it's all relative with time, discharging time. But initially, you will discharge those who easily discharge your flywheels and so forth. And then obviously, if the frequency still does not, if more reserve are required, then you go up the scale. And then peak shaving is also one of the important things when it comes to the grid operation. So, for example, obviously here, let's say this is time, and then this part here, it's it's midday, right? So you'll find that with the most solar, for example, generation, if this is during the day, you'll find that it peaks somewhere here, right? However, people are not around during this time, during the day. They're probably at work, not at home. And those who are working at home, they are busy with their work. There isn't much demand. So what happened then? We have this surplus of energy. Hence, then we use battery to charge, to absorb. So the battery becomes like an absorber of energy when there is an excess generation. And then this is midnight when everyone is back. However, solar irradiation is no longer as it was during the day. Hence, then solar wouldn't produce, the required generation to meet the demand. So then what happened then? Then the battery that stored energy during the day then takes this energy and then discharges it here to meet the demand. So it's one of the techniques that can help in terms of renewables when we want to mix solar and storage, wind and storage. And then coming now to grid flexibility and coordinating planning, as again, flexibility is very important, especially in the modern power system, because flexibility is the system's ability to adapt to variability and uncertainty, especially uh, with obviously the challenges of inertia. I'm not sure, but seems like there's someone's mic open. Is there a question or
I've muted them, Samkelo, you can continue.
thank you. So, uh, so flexibility and inertia, a very important point, all right? Inertia, as we said, is the system's ability to resist the change. However, with the increase of renewables are increasing. The last week, ECST and EIT were at the Solar and Storage Live Africa show, where there were discussions about renewables, and also IEA, IRENA, they are projecting that the increase is continuing of renewables. In most region, it is expected that at least 40% of electricity will be coming from renewable. And already experts are saying that the moment the grid passes the 40% of renewable share, it becomes difficult to manage the grid because the inertia has significantly decreased. So inertia, when it decreases, hence then flexibility becomes very, very important because then it becomes the grid's ability to adapt to that variability and uncertainty that comes with renewable, because renewables, they're inherently unreliable, they're inherently variable. So their generation fluctuates. You can never even really predict or forecast, even if you were to have your algorithms to incorporate weather data or previous historical weather data. You can never be sure as you would be if you were predicting uh, um, generation of your typical conventional generator, maybe using coal or using gas or nuclear, because those are dispatchable, right? Those you are able to just call them on the system. Whereas with renewable, you just have to wait for the solar radiation, to do it best and the way, and then you can try to store it if you don't need it at that time. So it changes the whole game when it comes to transmission, asset management. So again, that was regarding flexibility. And again, you can see here, this curve here, you can see the demand, which is this curve here. However, look at the generation. Look at this generation. This is due to renewable, right? This is due to renewable. So it's changing and changing and changing. So at some point here, here's our demand, and then there's a shortage. However, our demand now, it has to be met by storage and also flexible energy generation. Anyone who knows perhaps one of the common flexible energy generation, there's this generation, they tend to people talk a lot about it, that complements renewables so great, especially with what happening in the Middle East. Let me give you a clue. Anyone? Thank you, Promise, for your answer. I see your answer. You asked one of the previous question. Yeah, the closed loop is beneficial, and it is low cost in the long run. That's the good thing about pumped hydro. Anyway, to give you an idea, when you speak about flexible generation, so you speak along the lines of what? Natural gas. However, for those of us who are in South Africa, majority, in fact, I think about 98%, the last time I read this, about I think 98 to 100% of our gas we get it from outside, right? Is it Mozambique? We get it from outside, so we export our gas. And we see what's happening with oil, right? Imagine like depending on oil for fuel and all of that. So if the same thing were to happen with gas, you'll find that in most countries in Europe, they depend on natural gas. And during the time of Ukraine and Russia, we saw what happened. Some countries were strained because they couldn't get the supply of gas. So if something were to happen here in the SADC, you know, touch the wood, let's say let it, let's say maybe there'll be geopolitical um, issues or whatsoever. It means that we might end up not getting that gas. However, gas is very good when it comes to flexible generation because then it's able to complement a renewable. However, with a country like ours, it's a matter of it is an option. However, it constrains us, especially if we were to think in terms of sustainability. It might work now, but what about our children in future? Should anything happen in terms of geopolitical and all that? So then we have to then think of other flexible energy generation. And feel free to drop on comments on other sources that can complement storage. And someone could argue that we have an abundance of coal, and and perhaps they could advise how about we focus on clean coal technologies, because we see now with Japan and China, as much as they are largest emitters in the world, but now they're investing in clean coal technologies, to reduce emissions, because we don't have a coal problem, we have an emission problem. So again, at this point, clean coal technologies are still in development and they're also expensive. So those are some of the things that we should think about when you think about, uh, or these are the things that grid operators, uh, generation plans, they have to navigate from day-to-day operations to planning for days and months. And then again, it's all about coordination between generation, storage, and demand side management. So we have to find a way when it comes to generation, to coordinate renewables and storage and grid operation. And then obviously storage then can come in terms when renewables are not generating a required power. Obviously, we know that renewable and storage will not be enough because storage can store so much. Hence why I ask, what are some of the sources that we can consider? However, in mind, we have to have in mind that whatever other sources that we then have to consider, they have to produce less emission. They have to be economically viable, and also they have to ensure energy security. Hence, that becomes the so-called the energy trilemma. Then how we balance environmental safety, energy security, and also economic viability. Because you'll find in most instances you get two of the three. It's difficult, it's very rare to get a source that balances all the three. So it becomes then a game of balancing the three, which is also sort of like a challenge that grid operators all over the world are currently facing in this energy transition. And then the other important side, which is demand side management. You know, we're introducing this concept of demand side management, even though it's something utilities and companies were doing, where if there is a high demand then generation, then the utility will ask them to sort of, to disconnect. However, now even customers, residential customers can have this. There'll be we've seen an example just now in America, even though in terms of residential, it's still not a common thing in terms of residential customers, but the idea of demand side management uh, is to simply to volunteer to disconnect from the grid during the peak. Obviously, this comes with incentives. Perhaps you would then get power at lower tariff during off-peak. Um, so you could ask yourself then what's the difference between load shedding and demand side management? So load shedding is involuntary. Again, we might confuse that with the blackouts. Remember, if we could go back, blackouts they happen suddenly, unexpectedly, and everyone is cut off. Load shedding is planned, however, it is involuntary. Whereas with demand side management, it's the customer that says, I will disconnect to reduce the stress on the grid. Obviously, then you get incentives, you'll be paid for that, and also you or you will get electricity at lower tariff during off-peak. So these are all components that are important when it comes to grid flexibility, or that will ensure grid flexibility. And then this is an example in New England in America. So they are independent system operator. It shows then the breakdown of demand response. So we see customer facilities here. These are the loads, customer facilities, which then give up the power. So these are a demand. The initial phase is called the demand um, response asset. I'm not sure if it's clear here. Demand response asset, and then obviously, then you join this to get demand um, response resources. So demand response resources is a group of these assets. You have to group them first into about 5 megawatts or more for them to participate in the energy market. Then they are called the demand response resources. And then if you wanted then these demand response resources to participate in the capacity market, where here in the energy and reserve market is more about giving up power to the other loads nearby. And then the capacity market is sort of like the oral market. With this now capacity market, you have to then comprise these uh, demand response resources to make the active demand capacity consumer. So this is the whole hierarchy of demand response. And then here we see here seasonal and peak power plants. So obviously demand side management assist in terms of peak power plants. So normally if there is a demand that exceeds generation, what the operator will do, they will bring in initially the peak power plants, your diesel power plants, your hydro. We use hydro for peak power plants. So these are able to respond quickly if we see that, because we majority of our fleets, about 80%, the last time I checked, is still coal, right? So if our coal, which supplies our base load, if it happens then that the system is stressed because it it produces less than what's the system demands, then we bring our diesel, we bring in our pumped hydro, all those peak plants, to help in meeting the demand. And then with the demand, with this concept of demand response, then we are also assisting in that. And then going to economic and policy considerations, again, lithium-ion battery have always been expensive, but recently they've been a decline in their costs. Obviously, this is due to economies of scales since there are more deployments. And also, if you're to think of all the incentives the governments, that are putting in place to ensure that these transitions they do happen. And on your right, you see one of the interesting graph. So this is one of the very interesting formulas when it comes to determining the economic viability of a plant, the levelized cost of energy. You will see with lithium ion, which is yellow, you see it's sort of like constant, right? Initially, it costs a low, and then it stays there. Whereas with pumped hydro, look at where it starts. It is high upfront cost, because remember you have to find a specific geography, you have to build the structure of reservoirs, you know, all those things. Initially the costs are high, but if you look at with time now, so with time obviously that includes paying back the initial cost, operation and maintenance, and all that. But with time, the cost decreases. So here's the cost, and then here's the time. With time, it decreases. And then your battery, if you were to look at it initially, they're sort of affordable they're affordable in comparison to the other storages. However, in time, they are more expensive. So that's the levelized cost, because you have to maintain them, maintenance cost. At some point, obviously, you have to replace them. So yeah, so this is very, very interesting when it comes to determining the viability, and this also in terms of storage, by the way. this side here. So it shows price in relation to 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 the period and also in terms of storage. And then normally storages you find that they will provide ancillary services. So when you speak of frequency regulation, as a response to frequency, deviation, and also if you to think of then pumped hydro, they they drive generators which are asynchronous, so which also provides the inertia, and also if you to think of synchronous condensers, and also if you to think in terms of capacitors, that will be regarding then voltage control. So in essence, they provide these ancillary services, which are sort of like, I wouldn't say add-on because they're important to the system, but they come in whenever there is a need for them to come in. And one thing about when they operate as this is that they even get to get the payment capacity. So it means even if, for example, it's a peak time and obviously they haven't been called to supply the power, but they can still earn for the fact that they are running, they are ready to supply the power into the grid. So that in terms of market mechanism. And then in terms of policy frameworks, which is also a part when it comes to these transitions, there's a lot from integration standards, which is a work in progress, in terms of compliancy, then um, grid operators all over the world, they're still finding ways, they're still, testing to see in terms of code and how to integrate renewables and grid, renewable storage into the grid rather, and also in terms of regulations, standardizing processes and all, and benchmarking. So that's still all work in place. And then for the policy side, that will be your incentives again, your subsidies, your grants, all to encourage that deployment of these technologies. So all of this plays a part, by the way. It plays a big part because obviously if the government does not come into the part wherever in the world, then investors will not come into the part as well. So you will have these power purchase agreements and all what's happening in our countries currently, as we know that we have IPPs, uh, which are individual power producers, which are now connecting to the grid to assist in terms of generation. So there has to be agreement now because now we are having this public-private sector partnership. So there has to be a lot of agreements in place. There has to be benefits for the private to invest in the public infrastructure. They have to be, so government have to give incentives. They have to, subsidize, put agreements in place. Because, for example, now, if for example, here in South Africa, then ANC loses and another party comes in. There has to be an agreement that will ensure that whatever was planned continues even after this administration. In fact, anywhere in the world, even in America, if Trump administration comes to an end, um, or rather, let me just use UK because I'm not really familiar with the system operation in America. For example, in the UK, because they've done this privatization a long time ago. So in the 90s or in the 80s during Margaret Thatcher's administration, that's when what's happening in SA now happened that time in the 80s when they sort of privatized their power production. So whatever is in place throughout administration stays, to keep that confidence of investors in the public infrastructure. So the same thing here as well. That's where then policy and all that comes in place. And then this is one of the examples. So this is Hornsdale Power Reserve Project, Tesla's largest utility scale battery, which is in South Australia. The last time when we spoke about integration of renewable, if you remember, one of the case studies was what happened in 2016 when there was a natural disaster, there was lightning, and then their power lines was downed. So it means that transmission the part or the transmission assets, um, or lines rather, there was somewhere down. So it means its capacity was no longer the same. And then what happened then with the wind, it then forced more generation of wind power. So there was more wind power generated in this transmission asset, which lost some lines due to this natural disaster, which then led to a cascade. If you remember the second webinar. Um, so obviously, then this came a year later. It was still in the build. However, it got commissioned a year later. So to support the grid in terms of stabilizing and all that. However, with the recent incidents, then it has been able, or rather, it was able then to act as a shock absorber, obviously then supplying frequency response. So at this point when this was published, it was 100 megawatts. However, since 2020 is about 150 megawatt, it has been extended. It's all about, the drive to support the integration of renewable and to also prevent blackouts. So you can go read on it. It's one of the interesting projects is in South Australia. I came across it and I thought of the case study that we touched on the second webinar we had. And then these are our pump storage. So we have one in Drakensberg, Ingula, then we have Palmit pump storage. So these are our very own, obviously operated by Eskom. So as I've said, so far, these are used as our peak power plants. So when there is an exceeding demand, then we bring them in. So these are closed loop. As I've said, South Africa is semi-arid. Hence, you find that we have closed loop pump hydro. We don't have your typical hydropower plants where there's just a flow of water, a flow of body. We have two reservoir, obviously saving water, and it's a matter of then give and take. When there is demand on the system, we release the water from high reservoir to low reservoir, which then run the generators by spinning the turbines, which produce electricity. And when there is a less demand in the system, then the generator or then the generator acts as a motor and draws the electricity in to drive the pump to pump the water up to back to the upper reservoir. So it's a method of give and take and using potential energy and kinetic energy. So potential in terms of heights from high to low, and then kinetic in terms of water driving the turbine to generate electricity. However, these three will play a crucial role, especially with our I wouldn't say reform, even though our wholesale market, our wholesale electricity market is going through a reform, but I'm talking in terms of like what's happening with our transmission assets as we're integrating more and more renewables, especially regarding um, the National Transmission Company Transmission Development Plan. The latest one, we see that we'll be integrating more renewables, and also Eskom is also decommissioning coal plants. So there'll be a decrease. Um, uh, if I'm not mistaken, I think it is projected by 2030 to 2035, we will have less than what we have now. I think it will be less than 60 going to 50. So it means that more renewables will be added onto the grid. Hence, we will need these pump high storage to serve as storage backups. We've also seen some of their plans, which is regarding synchronous condense. It's regarding condensers, which are called synchronous condensers. We also touched on them on the second webinar, which will be then providing the inertia, the spinning inertia, and also with nuclear as well. Uh, so far we have Coburg, but there are plans of then having another nuclear plant. With natural gas power plants, we saw what happened in Richards Bay. Environmentalists, just as it happened with the nuclear, there's oppositions. So there's a lot happening. So there's also that part as well of environmentalists, where there'll be oppositions in development of other types of generations. And then, so in essence, the future outlook Really, it's more about the emerging technologies. We saw the solid state provides a safer option in comparison to lithium-ion batteries. However, they're still in development, and also in terms of vehicle to grid and vehicle to grid, where then we talks of EV, which is I know it's sort of a dream in this day and age. Um, However, the idea is then to charge your car if you are at work, then you drive it to your house, and then obviously when you get to your house, there's demand, there's still some power, then you can connect it to the grid to help to assist to reduce the demand, and then later after peak hours then you can charge this while you sleep, because car chargers take about 8 hours, right? Well, the AC ones, and then the DC ones that will be along the lines or along the roads will be your DC. It's interesting. One of the people we met in the solar show was the grid cars, who are busy deploying these power stations or charge stations. Um, so you can even check their map as well along South Africa. Obviously, most of it is in Johannesburg, Cape Town, Durban, your typical cities. So these are technologies that we are looking forward to. And that will be all for today. I'm not sure if there are any questions. I see we have 9 minutes. Busi, back to you.
Thank you very much, Samkelo. All right, as promised, that was a very engaging and very interesting topic and presentation. Thank you very much, Samkelo. There aren't any questions, but before we get to questions, just a reminder, just please type your questions in the chat box and then I'm going to read them out now. But just a few items to get through before we get to question and answer. We've got an upcoming course. So we have one of our accredited programs, the Bachelor of Engineering Technology in Electrical Engineering. If you found an interest in the presentation today, please, if you know anyone that is interested in enrolling for a BEng Tech, we are taking students. So we've got an upcoming enrollment on the 3rd of August. So just please go onto our website. There you will find an application form that you can complete. And if you just want information, you'll also find our program advisors' contact details. They will call you and advise as to a way forward if you are interested in enrolling. And then upcoming webinars as well as events. We've got 2 more webinars that are upcoming. The first one being on the 15th of April. This is the fundamentals of electronic systems. The next being the 29th of April, protection and reliability in electronic systems. And then we also have an open day that's upcoming. This is taking place on the 23rd of May. This will be an in-person open day. So please feel free to come onto our campus and we will also just show you around the campus. You'll get to engage with us in person, ask as many questions as you want. We'll also just be putting on presentations and showing you around our workshops. So you get to get a feel of the campus. So please do attend and share the word that we've got an open day taking place on the 23rd of May. All right, and earlier I informed you about that certificate of attendance. This is a QR code as well as the link. So just please take the time to scan this. It will take you to, I think, an information form where you need to complete your information in order to request the certificate. So if you can just please do that, I'm going to leave it. I'm going to leave the slide on as we attend to the question and answers. If there are any, please put them in the chat box or just raise your hand and then I will give you the floor. Samkelo, were you happy with the answer that you gave to Promise? Do you want to maybe engage more?
No, I'm happy with it. I think she answered me correct. Well, not there isn't a correct answer, but I think she answered me fully. you know, because obviously it was a question that we said we will reflect on towards the end or at the end of the webinar presentation. So she ticked two of them, long duration and low cost. So in essence, pumped hydro storage is mature in terms of like all the other storages. You know, your battery technologies are still catching up, even though there is a decline in their cost, but they're still catching up in terms of levelized cost. We see that in in long term, even though it is the cheapest initially, lithium ion, but in long term, it remains the most expensive option from that graph. So the other technologies are still catching up in terms of maturity, in terms of economy, in terms of also of scalability. It's quite a challenge to scale lithium. We saw that even flow batteries are easier to scale than lithium. And also lithium has a lot of, in terms of its ability to keep storage, that too is also a factor as well. And also it has leakages. So there's a lot happening with lithium as much as obviously it sort of comes next after pumped hydro. But in the long term, it's costly or more expensive to maintain. So I think she answered, like fully answered. The two important, long duration and also low cost. That's are the things we are looking for in terms of grid balancing or grid stabilizing. And then obviously lithium most of the time is used for short term, for example, short term response, your electric cars, and maybe just short term balancing of the grid. But however, we want something that we will use in the long term, in the long run. So then things like pump hydro storage will be the things we want to have.
Thank you very much, Samkelo. There still isn't anything in the chat box. I'm just going to display our contact and information resources. Again, as mentioned, if you want to access our website, if you want to complete an application form, or if you just want to learn more about the campus, just please access us through this website here, this www.ecst.ac.za, or you can just call us. There's always someone around to answer your call, and again, just answer any questions that you guys might have. I hope you guys were able to scan and copy the link for the certificate of attendance. But if you didn't, again, as indicated earlier on, we will be sending you this presentation. So you can also just access the presentation once you get it and scan the QR code as well as access the link. If there isn't any questions, we still have 2 more minutes. If there aren't any questions, I think we can close. Samkelo, is there anything that you would like to add before we close?
No, but just to thank everyone for joining us today. And I think there will be sort of a link that they will get in terms of comments. I also look forward to that. Perhaps some might feel perhaps I could have went even deeper or any suggestion on future topics. Yeah. Thanks everyone for joining us. Enjoy the rest of your week. Enjoy your holidays. Take care.
All right. Thank you very much, everyone. See you guys on the next one.
Thank you.
Thank you.